Hi, my name is Joshil Vaddi, and this is my black hole lab. Introduction. So, the brief purpose is to determine the mass of the black hole. We want to determine the gravitational forces of the black hole and the planet, and determine the initial velocity of the ship in order to escape the black hole and avoid the planet. So, the results of this lab include the mass of the black hole being 4.39 times 10 to the 23rd, and the velocity of the ship being negative 1.02 times 10 to the 8, and 2.53 times 10 to the 8. And then the z direction, the velocity is 0. So the principles and important concepts that we need to know. We need to know the impulse momentum formula, such that F net is equal to delta P times delta T. We also need to know the momentum equation. P is equal to mass times velocity. Another important thing to note is that the net force in the perpendicular direction plus the net force in the parallel direction is equal to the total net force. Finally, in order to update the position of entities such as a spaceship, we need to use a position update formula and the velocity update formula in our code. We also need to use a force of gravity equation, G m1 m2 over r squared times r hat, in order to update the gravitational force of the black holes and star and other entities. And it's important to note that we are using uniform circular motion, where the F net parallels is in the direction of the velocity, and the centripetal acceleration is the F net perp, or F net perpendicular. The systems and surroundings of our part 1 coding is the system being the star and the surrounding being the space and the black hole. For part 2, our system is a star and planet, while the surroundings are the black hole and space. Our part 1 initial conditions include our star mass being 2 times 10 to the 30, our delta t equals 5 as a time interval, and our time for first observation being t equals 0. We'll also increment the time with the delta t, so it increments plus 5. And now our equations and code. So we use the momentum formula to compute our p initial and p final. We also calculate the star's changes in velocity, v final minus v initial, p final minus p initial. We then use Newton's second law to calculate F net using dp dt, which is equal to the net force in the parallel and perpendicular directions. We then use Newton's second law again to calculate F net in the parallel direction and F net in the perpendicular direction. And then we finally use this to calculate the total net force. We also calculate the mass of the black hole using the magnitude of F net times the magnitude of the star's positions divided by the force of the gravitational force. And we also have arrow scales here. And our part 1 results show that the net force was 2.73 times 10 to the 8. The F net parallel was 1 times 10 to the 8. F net perpendicular 2 times 5, 3 times 10 to the 8. And the mass of the black hole was 4.39 times 10 to the 43. So some potential sources of error include rounding values for steps and errors with time intervals. So our part 2 initial conditions are, so black hole mass again was 4.39 times 10 to the 43rd. We have our gravitational constant, the mass of the planet, mass of the ship, which are already updated there. Then we use the initial conditions, planet speed. We use a formula. We took the square root using the FG formula. And then we updated the velocity. Next, we have the coding part. And this is where we use the net force on the planet, and we use the gravitational force. So, for example, we tried to find r hat. We found the masses. We multiplied that in order to find the forces on the ship on the planet, the force of the black hole on the planet on the ship, and we used the force of gravity equation to do that. And then we also applied Newton's second law and the position update formula to make the planet and the ship move. We also use a velocity update formula for this too. And so the results, calculations finished after 10 minutes. Our final ship position is 1.67 times 10 to the 11. And sources of error, and some sources of error include rounding errors as well as mathematical errors. And something also to note is that in here we try to find the net force in every single direction. For example, the ship to the planet and the planet to the ship and all of this. We can find the total net force of the entire system and use that. So what does it mean and what if? So the net force is actually equivalent to the rate of change in momentum by Newton's second law. And this is because force is equal to ma, and that's also equal to dp over dt, which can be simplified into the parallel and perpendicular components. And the rate of change of momentum is equal to the parallel and perpendicular components combined, or the total net force. Now we look at what if. Well, a more vertical velocity would be required because we need more perpendicular velocity and less parallel velocity in order to portray a new velocity that would accurately describe the question. And so our new velocity would actually have an x component of 0.98 times 10 to the 8. Thank you.